In this video, I'm going to talk about the concepts of the Poisson distribution. To understand the Poisson distribution, we can firstly understand this situation. Suppose a call center can receive a call and at most one call at any instant. That means it cannot receive two or more calls at the same instant. Also, each instant is independent and has the same chance of getting a call. In other words, in terms of probabilities, each instant is independent and identical. Suppose it is further known that on average, the center receives 20 calls in 1 minute. That means the expected number of calls in any minute is 20. Now we let x be the number of calls received in 1 minute. So what is the probability distribution of this random variable x? To calculate the probability distribution of x, we can consider a limit like this. We let n be the number of equal intervals in 1 minute, and let xn be a binomial variable with parameters n and p equals 20 over n. In this way, the expectation of xn equals np equals 20, which is the given expectation of x. That means when I take the limit of xn as n approaches infinity, I can consider the infinite instants in 1 minute. And each instant is just like a Bernoulli trial. Also, the expectation obtained here can match the average number of calls given in the situation. So that means this limit of the binomial variable xn as n approaches infinity is exactly the random variable x that we are interested in. As a result, now the probability that capital X is equal to small x is just equal to the limit of this binomial probability as n approaches infinity. After rewriting the expression in this way, we can actually obtain the number e in this limit. Therefore, we can get that the probability that capital X is equal to small x is equal to e to the power minus 20 times 20 to the power x over x factorial. And the possible values of x are 0, 1, 2, so on and so forth. Theoretically, x can be infinitely large. Hence, we can successfully obtain the probability distribution of x in this situation. From this result, we can see that there is only one parameter in this distribution, and this parameter is the expected number of calls in 1 minute. In other words, in any situation like this, by just knowing the expectation of x, it is already sufficient for us to obtain the probability distribution of x completely. In probability theory, this distribution is known as the Poisson distribution, which is named after a French mathematician. And we can use this notation PO bracket 20 to denote that x follows the Poisson distribution with parameter 20. In general, we usually use the Greek letter lambda to denote the average number in the Poisson distribution. So if the call center receives lambda calls in 1 minute on average, we can know that the probability that capital X is equal to small x is equal to e to the power minus lambda times lambda to the power x over x factorial. Now let's take a look at the expectation and the variance of a Poisson variable. For the expectation of x, it is obviously equal to lambda, as it is our assumption throughout this situation. And then for the variance of x, similarly, we can consider it as the limit of the variance of the binomial variable concerned. So it is equal to the limit of np times 1 minus p as n approaches infinity, like this. As a result, we can see that the variance of x is also equal to lambda. Hence, we can obtain these simple results. We know that both the expectation and the variance of a Poisson variable are equal to lambda. Another important characteristic of the Poisson distribution is that the average number is scalable with respect to the length of the time interval. For example, if the average number of calls in 1 minute is lambda, then for 2 minutes, the average number is just 2 lambda. And the distribution of the number of calls in 2 minutes is still a Poisson distribution. The only difference is just the parameter here. Now it becomes 2 lambda. And so the new probabilities, the new expectation, and the new variance can be obtained like this. Similarly, for 0.5 minute, the parameter of the Poisson distribution becomes 0.5 lambda like this. In general, if lambda is the average number for 1 minute, then for k minutes, the random variable will follow the Poisson distribution with parameter k lambda like this. Finally, let's take a look at this example to consolidate our understandings of the Poisson distribution. Suppose the number of telephone calls coming into an inquiry hotline in a minute follows a Poisson distribution with a mean of 1.2. In part A, we need to find the probability that no calls come into the hotline in the next minute. We can consider a random variable x, which follows the Poisson distribution with the mean for 1 minute, which is 1.2. Then according to this formula of Poisson probabilities, the required probability is the probability that x is equal to 0, which is simply equal to e to the power minus 1.2. As a result, it is equal to 0.3012, correct to 4 dp. In part B, we need to find the probability that more than 3 calls come into the hotline in the next 5 minutes. Now we can consider another random variable y, which follows the Poisson distribution with the mean for 5 minutes, which is 6. Then the required probability is the probability that y is greater than 3. Here we can consider this probability as 1 minus the probability that y is equal to 0, y is equal to 1, y is equal to 2, or y is equal to 3. This calculation seems complicated, but if we treat this factor e to the power minus lambda as a constant that can be taken out, then the sum of these 4 Poisson probabilities can simply be written in this way. This part in the bracket is indeed the sum of the first 4 terms in the expansion of e to the power 6. So we can observe a really nice pattern here. As a result, the required probability is equal to 0.8488, correct to 4 dp. Lastly, in part C, we need to find the expectation and the standard deviation of the number of calls in the next 45 seconds. In this case, we can consider another Poisson variable k with the mean for 45 seconds, which is 0.9. In this way, the required expectation is simply 0.9, and the required standard deviation is the positive square root of the variance 0.9, so it is equal to 0.9487, correct to 4 dp. This is how we can understand and apply the concepts of the Poisson distribution.